100 million gallons. That is the volume of water required to bring a 1,000-foot-long steel mountain back to life. In April 2024, the USS John C. Stennis, a 100,000-ton nuclear warship, emerged from a 4-year engineering coma that would have bankrupted a small nation. Right now, the USS Ronald Reagan is sitting in an identical concrete tomb. Stripped, scarred, dead. Getting it back into the same form is where the real danger lies, because the margin for error is razor thin. A single miscalculated valve, a shifted center of gravity, faulty weld, and the pride of the U.S. Navy becomes a 13-acre catastrophe. This is what it actually takes to bring a supercarrier back from the dead. When a Nimitz-class carrier enters dry dock, it isn't for a tune-up. It's for an RCOH, refueling and complex overhaul. Think of it as a heart transplant, a brain upgrade, and a skin graft all happening at the same time. For the first 25 years of its life, a carrier is a workhorse. But by the quarter-century mark, the nuclear cores are running low, the electronics are aging, and the hull has seen thousands of miles of saltwater abuse. This is when the Navy hands the keys over to the shipbuilders at Newport News. The scope of work is staggering. The ship's heart gets cracked open to replace the spent uranium cores, a process so sensitive it requires its own specialized security and engineering teams operating in near-surgical conditions. Then comes the total modernization. Miles of 1970s era copper wiring ripped out and replaced with fiber optics and state-of-the-art radar arrays. And while that's happening above the waterline, every square inch of hull below it gets blasted, inspected for micro cracks, and repainted with high-tech anti-corrosive coatings. From the inside out, this ship is being rebuilt from scratch, and it's not just the systems below deck. The island, that iconic tower rising from the flight deck, often gets heavily modified or partially reconstructed during this period to accommodate new radar arrays like the Spy-6. What looks like a simple antenna upgrade from the outside is in reality a complete structural surgery on the most visible part of the ship. But here's the part that most people miss. While the ship is in dry dock, it is technically dead. It has no power of its own. It relies on massive umbilical cords from the shore for electricity, air, and water, kept alive on life support like a patient mid-surgery. The crew, nearly 3,000 sailors, essentially becomes a construction crew. This is a gritty, loud, and dangerous environment where thousands of civilian contractors and uniformed personnel move like a synchronized army of ants every single day for years. But before any of this work could begin, the ship had to be lowered into something that makes even seasoned engineers go quiet, a concrete tomb the size of a city block. To understand the rollout, you have to understand the cradle it sits in. Newport News Shipbuilding's Dry Dock 12 is the only place in the Western Hemisphere capable of this feat. It's 2,172 feet long, large enough to fit the Empire State Building with room to spare. When the ship first enters, it's a game of inches. Tugboats nudge the carrier in with less than 3 feet of clearance on either side. Once the gate, a massive steel caisson, is sunk into place, the dewatering begins. As the 100 million gallons are pumped out, the carrier slowly settles onto the keel blocks. These aren't just piles of wood, they are precision-engineered pillars of concrete topped with soft timber, specifically positioned to match the ship's internal structural ribs. If a single block is off by even a few inches, the weight of the 100,000-ton hull can cause the steel to oil can or buckle. Imagine placing a bowling ball on a dozen toothpicks. If they aren't perfectly aligned, the ball crushes them. Now multiply that by 100,000 tons. And after years inside that tomb, the moment everyone has been dreading and preparing for finally arrives. Fast forward 4 years, the Stennis is gleaming with new paint. Radar masts are updated, propellers, each one a bronze masterpiece weighing roughly 30 tons, are polished to a mirror shine. Now comes the moment everyone has been sweating over, the rollout. But you don't just open the gates. First, the engineers have to play a high-stakes game of physics Tetris. During the years of repair, thousands of tons of equipment were moved. New electronics were added, old pumps were removed. This means the ship's center of gravity has shifted. If the cog is too high or too far to one side, the ship will loll, tip the moment it lifts off the blocks. To prevent a catastrophe, the Navy calculates the metacentric height using internal ballast tanks, filling some with water, keeping others empty to ensure the ship has positive stability. They are essentially balancing a skyscraper on its side so that it floats perfectly level. But there's another variable most people never hear about. The ship has to be trimmed stern down, meaning the back of the vessel sits fractionally deeper than the front. It sounds minor. It isn't. Without that deliberate tilt, the ship can wander as it gains buoyancy, drifting unpredictably inside the dock before it's even free of the blocks. It's a mathematical tightrope walk where the prize is a functioning carrier and the penalty is a multi-billion-dollar catastrophe. Then there's the underwater inspection. Divers and robotic crawlers do one final sweep of the hull, looking for anything: a stray tool, a forgotten piece of scaffolding, a faulty sea chest valve. Once the all clear is given, the silence of the dry dock is broken by the roar of the intake valves. Now, the only thing left is to open the valves and let physics decide if they got it right. The day of the flooding is not a celebration, it is a controlled crisis. At Newport News, when they crack the intake valves of Dry Dock 12, they aren't just letting water in. They are inviting a massive physical force to reclaim the ship. Of the entire operation. As water reaches the hull's lowest openings, the sea chests, the cooling intakes for the nuclear reactors, engineers are already positioned deep inside the ship's bilges, crouched at the very bottom of the hull watching. They are looking for a single drop of moisture where there should be none. One failed valve at this stage is recoverable. They can still pump the dock dry in hours and fix the problem. But if that same valve fails later, this ship becomes a 100,000-ton bathtub. So they watch and they wait. Then, somewhere around the 30-foot mark, something almost imperceptible happens. The ship begins to lighten. It hasn't floated yet, but it's no longer crushing the concrete keel blocks with its full weight. And that's precisely when things get dangerous, because without the friction of its own mass holding it in place, a strong gust of wind or even a minor current could slide the entire carrier sideways, a 1,000-foot steel wall drifting where it shouldn't. To stop that from happening, massive steel mooring lines are tensioned to the dock walls, holding the ship in a kind of iron straitjacket, keeping the Titan exactly where it belongs while the water continues to rise. The mooring lines are screaming under tension. 30 feet of water now sits beneath a ship that still hasn't moved. What happens next has no second chances. There is a specific millisecond in the rollout process known as the critical lift. This is the exact moment the hull loses contact with the timber caps of the keel blocks, and the physics of what happens in that millisecond are something most people never hear about. After 4 years of sitting on those wooden-capped concrete supports, the hull doesn't simply pop off like a cork. There is a literal suction, engineers call it stiction, that develops between the hull and the blocks. As the rising water builds upward buoyancy pressure of millions of pounds, the ship resists. It stays stuck. And then, when the stiction finally breaks, the ship jumps. Not dramatically, maybe just an inch or two, but an inch of sudden movement in a 1,000-foot vessel creates a shockwave that travels through every deck, every bulkhead, every weld. This is why the crew was stationed at every void and compartment in the ship during this moment. If a seal fails during that jump, the ship starts taking on water in places that are supposed to be bone dry. For the engineers on the docking team, this is the ultimate test of their math. If the ship was loaded unevenly during the 4-year overhaul, perhaps too many pallets of spare parts stored on the starboard side, the carrier will list, tilting the moment it floats free. Even a 1-degree tilt on a ship this wide can cause the flight deck to overhang the dock walls dangerously. Once the ship is off blocks, the divers go back down. This is a job for the bravest souls in the yard. They swim underneath 100,000 tons of suspended steel to ensure no blocks have stuck to the hull and that the sonar dome, the sensitive bulbous bow of the ship, has cleared its cradle cleanly. Once the clear signal is flashed to the bridge, the carrier is officially a vessel again. But it's a vessel without a brain. The nuclear reactors aren't online yet and the propellers aren't turning. It is a 1,100-foot long dead stick, completely at the mercy of the elements. Moving a dead carrier out of a narrow concrete slot is the world's most expensive game of operation, and to pull it off, the Navy deploys a fleet of tractor tugs, stubborn, high-horsepower boats that can rotate a full 360 degrees on a dime, each one essentially a controlled explosion of thrust wrapped in a steel hull. When the USS John C. Stennis rolled out, it took nearly a dozen of them, and every single one had a specific job. At the front, the lead tugs did the heavy lifting, pulling the carrier forward, coaxing it toward the James River with slow, deliberate tension. Along the flanks, positioned at both bow and stern, the flanking tugs worked like hands on a steering wheel, nudging the ship left or right in real time to keep it perfectly centered in the channel. And at the rear, a final set of tugs did something counterintuitive. They pulled backward, acting as brakes, because 100,000 tons of steel moving at even 2 knots carries enough kinetic energy to punch through a concrete pier like it's made of toothpicks. What makes this genuinely terrifying is the clearance. At certain points during the extraction, there is less than 24 inches between the carrier's hull and the edge of the dock. 24 inches. That's roughly the width of a carry-on bag, standing between a flawless operation and a catastrophic, career-ending mistake. One miscalculation by a tug captain, one snap of a tow line under tension, and the Navy isn't just looking at a repair bill, it's looking at the kind of headline that makes senators call emergency hearings. Exiting the dry dock is a milestone, but it's only the 60% mark of the journey. The ship is now moved to the outfitting pier. Think of this as the interior decorating phase. If interior decorating involved installing 20mm Phi-length CIWS cannons and calibrating 3D air search radars, this is where the ship stays for another 12 to 18 months. Why so long? Because the nuclear steam plants have to be slowly brought back to life. You don't just turn on a nuclear reactor. It's a weeks-long process of heating systems, checking for thermal expansion leaks, and eventually spinning the 4 massive bronze propellers for the first time in years. This is the phase where the ship's force, the sailors, reclaim their home from the civilian contractors. They start living on the ship again, eating in the mess decks and sleeping in the berthing areas, testing every toilet, light bulb, and computer terminal. So, the Navy doesn't like to broadcast. The United States is running out of places to put these ships. While we have 11 nuclear-powered aircraft carriers, we only have 4 public shipyards capable of performing this level of deep tissue surgery. Norfolk, Portsmouth, Puget Sound, and Pearl Harbor are the only holy sites of carrier maintenance. But there is a silent killer stalking these facilities. Age. Most of these dry docks were built during or shortly after World War II. They were designed for ships half the size of a modern Gerald R. Ford-class supercarrier. Today, the Navy is locked in a multi-billion-dollar shipyard infrastructure optimization program, SEOP, just to keep the concrete from crumbling. In places like Puget Sound Naval Shipyard in Washington, the situation turned from urgent to critical in 2023. Engineers discovered that the dry docks, the very ones currently holding our West Coast carriers, sit on a major seismic fault line. If a significant earthquake hit while a carrier like the USS Ronald Reagan was on the blocks, the dry dock could literally crack like an egg. 100 million gallons of the Pacific Ocean would rush in instantly, potentially capsizing a 100,000-ton vessel inside its own cradle. Because of this, 4 dry docks were abruptly shuttered for emergency seismic strengthening. This created a massive traffic jam in the Pacific. It meant that any carrier needing a rollout had to wait in line behind attack submarines that were already years behind schedule. Currently, nearly 36% of the U.S. submarine fleet is sitting idle, waiting for a parking spot in a dry dock. For a carrier, that delay isn't just an inconvenience, it's a gap in national security, which is why when a carrier finally gets its turn, they push it to the edge of breaking before they trust it with a war. Once the carrier leaves the outfitting pier, it enters the most intense phase of its resurrection, the fast cruise. Imagine being stuck in a house for 4 years while contractors replaced every wire and pipe. Now, imagine trying to live in that house while it's moving at 35 miles per hour through a hurricane. That is the fast cruise. For several days, the ship is tied to the pier, but the crew acts as if they are at mid-ocean. They dog the hatches. They run general quarters drills. They simulate fires in the galley and floods in the engine room. They are testing the human-machine interface. Does the new radar talk to the new missile launchers? Do the new electromagnetic catapult's emails have enough juice to launch a 60,000-pound F-35? Then comes the moment of truth. Sea trials. The tugboats finally let go. For the first time in nearly half a decade, The carrier's own 4 massive bronze propellers, each weighing 60,000 pounds, begin to churn the water. The vibration is felt through every deck of the ship. During sea trials, the Navy performs high-speed turns. They push the ship to its maximum flank speed, officially 30-plus knots, though everyone knows it's faster. They want to see if the hull shudders or if the new welds hold under the immense pressure of a 100,000-ton ship carving a U-turn in the Atlantic. If something is going to break, they want it to break now, while the shipyard engineers are still on board with their clipboards and sensors. When a carrier like the USS John C. Stennis finally returns to the fleet after its rollout and trials, it isn't the same ship that entered the dock 4 years prior. It is a digital warrior in an analog skin. The cost of this rollout process? For a full RCOH, the bill typically clears $4.8 billion to $5.2 billion. To put that in perspective, you could build a world-class stadium in every major U.S. city for the price of fixing one carrier. But for the U.S. Navy, this is the only way to maintain a 11-carrier Navy. Without these dry dock miracles, the fleet would shrink by half in a decade. These rollouts ensure that a ship built in the 1990s can still hold its own against hypersonic missiles and drone swarms in the 2030s. So, what happens when a gigantic U.S. aircraft carrier gets rolled out? It's not just a ship moving into the water. It's a testament to a workforce that refuses to let the iron giants die. It's the result of millions of man-hours, billions of dollars, and the kind of engineering that makes the impossible look routine. Every time a carrier like the Stennis or the Reagan clears the dry dock gates, the world changes. The balance of power shifts back toward the horizon. These ships are more than steel. They are floating sovereign territory. In the process of bringing them back from the dead, a floating 100,000 tons of nuclear-powered ambition is the greatest engineering show on Earth. If this is the kind of engineering that blows your mind, subscribe and drop a comment. Which carrier do you think is the most dangerous warship ever built?